This is first part of lecture 5. In this lecture, we will study fatigue failure when we have variable stresses. So loading in elements can be static or can be variable. Variable means load doesn't have one fixed value. It can increase and decrease. Increasing load and decreasing load will change stresses. Movement can also lead to variable stresses. When we have dynamic conditions, failure can happen even if stresses don't exceed ultimate strength. So failure happens after few cycles of changing load, and failure in this case is sudden. You don't get any indication, there is no warning, there is no visible indication that failure will happen. So failure is complete and sudden failure. Okay, so we need a method to study or to simulate fatigue failure when we have variable loading. We have a few methods, but in this course we will study stress life method, which is a simple, most traditional and easy to implement method. So in this method, we will link amount of stress with number of cycles we can apply that stress before failure. Okay, so the experiment that we're going to use is simply we prepare specimen that is carefully machined and polished with standard size. We actually need many specimens to run one experiment. This test specimen is subject to repeated stresses, and we must count number of cycles and before failure under specific stress. So the test machine here is called RR Moore high-speed rotating beam machine, and the specimen is subject to one type of stress, which is bending stress. So we apply bending here. When you apply bending here, you create compression at the top surface and tension at the bottom surface. Okay, so to start the test, the first run, we're going to apply stress here, bending stress, that is equal to ultimate strength. So what's going to happen? So even in this case, we are not rotating the beam still the beam is static, but once stress is equal to yield strength or ultimate strength, we will get failure, complete failure, even without running or without creating any stress cycle. Now we take a new test specimen, and in this case, stress is kept under ultimate strength, so we don't break the test specimen. Now we rotate this test specimen. When you rotate, and any point on the top surface here, which has compression stress, with rotating 1/2 cycle or 1/2 rotation, this point will move here, and instead of compression, it will have tension. So each point on the surface will go through compression, and at the middle there is no stress, at the bottom there is tension, and then no stress, and then compression, and so on. So it will have variable stresses, stress increase and decrease. Okay, so as you can see, my stress is less than ultimate strength, but this test specimen will fail after number of cycles. So we record that number of cycles. Okay, we repeat this test with many specimens. We reduce the amount of stress at each run. So when you reduce amount of stress, you get more cycles. Okay, so you record the number of cycles and stress of failure. You will get a curve something like this. So this is the SN curve, or strength in the vertical axis here, and number of cycles and the horizontal axis. As you can see, when number of cycles are 0, we got failure at ultimate strength. And then when we reduced stress just below ultimate strength, we managed to rotate or get few cycles of load before failure. Okay, so this region from here up to here is called low cycle region. Okay, we reduce stress, and reducing stress will increase number of cycles until we reach a point where we reduce stress to an amount that will not lead to failure. So that stress is called endurance limit. So if I go back to the previous slide here, if stress here doesn't lead to a failure, if we rotate, but no matter how many rotations you do, you will never break this element. When you reach that point, stress here is called endurance limit. Endurance is given this SE, that's endurance strength. Okay, so endurance strength is a value here. Okay, so this curve is very important. Each material will have its own curve. The curve here depends on the value of ultimate strength and the value of endurance limit. If you know ultimate strength, you can identify this point. If you know endurance limit, you can draw this line. This line starts from 1 million cycles. So any material that can give you 1 million cycles, you call infinite life. So a material will have infinite life if it can provide 1 million cycles. Okay, so now if you identify this point here at 1000 cycles, then you can easily complete the whole curve. Okay, so we need strength of failure at this point. Experiments show that endurance limit, value of endurance limit, is linked to the ultimate strength. So if you look at this curve, you see that is failure. All points here are failure, and all failures happen between 0.6 and 0.4 of ultimate strength. So strength or endurance strength is limited between 0.4 and 0.6. So it is safe to say that 0.5, which is an average between 0.6 and 0.4, 0.5 ultimate strength is equal to endurance limit. Okay, but if you have a very strong material with a strength of more than 1.4 gigapascal, then you just take this fixed value for endurance limit. So for any 1.4 gigapascal ultimate strength or more, your endurance limit will be 700 megapascal. Otherwise, endurance limit is 0.5 ultimate strength.